Good day, everybody. So let's take a look at certain questions and topics and problems related to introductory organic chemistry. And today we're going to focus specifically on alcohols and some of their reactions. So to begin with, we are going to take a look at nomenclature things, right? So we need to be able to name alcohols, and like one way to start going about naming of alcohols will be to consider an alkane as a backbone to which an OH group is attached, right? Alongside some sort of other substituents, be that maybe some kind of like alkyl substituents, or maybe aromatic ones as well, right? So yeah, because as I was saying, if we try to relate our knowledge to real life situations, so to speak, then in the real life situations, you will encounter a bunch of various alcohols, right? Not only it's going to be ethanol or isopropanol, which we can find in many different like mundane applications, grocery store, some sort of medical aid kit and so on, right? So, but also we need to be aware that many other alcoholic structures do exist out there. So, but for now, let's take a look at something like very basic. So this one will be looking like this, problem one. So item A, I would say. So we'll have a methyl group. Sorry for my crooked writing. So then we'll have like this, like that, and let's add another carbon, because why not? And the OH group will be here, right? So right now we can see that there are 5 carbons in the chain, right? So what does it mean if we have 5 carbons in the corresponding alkane? It means the name of this alcohol will bear the name of the corresponding alkane, which will be pentane, right? So, but of course, this name will be modified because now we don't have just an alkane, we have an alcohol, right? So still, however, the root of this name will remain. So in our alcohol name, right? So pen 10, right? So let's put it this way. So pen-10 as a root will be retained, right? Because we have the 5 carbons in the main chain of this alcohol. So then we have the alcohol, right? Which means we are going to have the suffix OL followed that follows the root of the name. So we'll have some sort of pentanol, right? So then we are going to number the carbons, starting with the terminus that is closest to the carbon to which OH group is attached, right? So as one of your peers mentioned previously, the OH group will have to have the minimal number, right? So if we start naming from here, let's say 1, 2, 3, 4, 5, then the 5th carbon will have the OH, right? So that's going to be like too high of the number potentially, right? So for the OH group position. However, if we start naming from here, from this end, right, and if we go ultimately right to left, then we are going to have 1, 2, 3, 4, 5, right? And then the carbon number 1 will have the OH group, right? So consequently, if we number the carbons right to left, the OH group will have the smaller number, which is going to be 1, right? So carbon number 1 will have the hydroxy group attached to it. Sorry. So consequently, we are going to have the number 1 in front of pentanol, and then it will basically tell us that carbon number 1 will have the alcohol group, right, or the OH group attached to this carbon number 1 in the backbone that contains total of 5 carbons and resembles the alkane. Basically, it's going to be saturated backbone. No double bonds, no triple bonds, no nothing of that kind. So 1 pentanol will be made, right? So now let's just take a look at some kind of like derivatives of this alcohol, or isomers in other words, and then we're going to have something like that, right? So it's going to be an isomer. So if you count the carbon atoms, hydrogen atoms, and oxygens, it's going to be exactly the same molecular formula for those 2 compounds, except the kind of like attachment of the atoms will be different, right? So just like when we look at those pictures and those drawings. So clearly the OH group here is on the terminal carbon. Here, the OH group is somewhere kind of like on the carbon in the middle, right? So, or in between the terminal carbons. So now let's try to name, right, or number this chain, right? So it's going to be the same chain, 5 carbons. So the pentane root will remain, okay? So now numbering wise, so what do we have? So we can either number from right to left. 1, 2, 3, 4. So carbon number 4 will bear OH group, or we can go left to right. 1, 2, 3, 4, 5. So in this case, if we go left to right, then carbon number 2 will have the OH group. So which gives us the lower number for the OH group carbon, right? So 2 will be preferential. It will minimize the number for the OH group. Consequently, we are going to have 2. So we are going to have the numbering from left to right. 1, 2, 3, 4, 5. So this will give us the second carbon as the one bearing OH group, right? So and that's it. So now let's put it together in the name, right? So carbon number 2 in the pentane derived chain, pentane, that's going to be the root, will have the hydroxy group, or it will have the kind of like alcoholic functional group located at carbon number 2, right? So this will be designated with the suffix "ol." So carbon number 2 will have the alcohol, right? So that's like one way to think about it. So, and overall, we'll have the 5 carbon chain in which kind of the hydroxy group, OH, is located to make the alcohol functional group and have an alcohol for us at the end of the day. All right, so now let's move on. Let's erase everything quickly here. I'm going to clear the board. So it's still problem number 1, but here we have slightly different situation going on. So now let's take a look at the aromatic substituent present in the main chain. So something like that, right? So here we have C6H5. We have 3 carbons in the main alkyl chain. We have the OH group, right? So we have an alcohol here. You can think about that, right? So if you look at the like building blocks, so yeah, because this kind of like skill like of looking at the building blocks will be translatable to like real life applications in, let's say, your professional careers, right? When you might encounter some sort of like new compounds, right, which you did not see before in like academic courses, let's say, right? So, but still, you can like decipher something about those new compounds which you encounter, let's say, in your medical practice, right? Or some sort of nutrition practice and so on, right? So the organic chemistry is applicable to those areas, for example. So yeah, here we go. So we have here, so apparently the alkyl chain, so it's saturated hydrocarbon chain, so no double bonds, right? So then we have the substituent here, such as C6H5. So if you write out the expanded formula for yourself, then you'll be able to count the carbons and hydrogens here, right, in this particular substituent, C6H5, which is also known as phenyl. Not phenol, but phenyl, NYL, right, spelling wise. So then we have our hydroxy group, which is OH. When it's bound to the carbon, right, in organic compounds, it's going to give a rise to alcohols, right? So we have the alcohol with the substituent, and now let's try to name this compound, right? So again, so once we name this, so we need to think about the numbering, so we can number either from left to right or right to left. So we're going to minimize the number of the carbon to which OH group is attached, right? So in terms of numbering, the positioning of the OH takes precedence over the positioning of the phenyl group or other substituents, right? So we mostly want to minimize the number of the carbon to which OH group is attached, right? So that's what we mean by OH group taking precedence, right? So we need to take into account this the position of the OH group, right, when we want to number the chain, right? And then we want to minimize the number of the carbon to which the OH group is attached, right? So that's kind of like complicated, but that's how it goes, right? So that's the rules. So again, if you name left or number, sorry, in the chain left to right, you are going to have the OH on carbon number 3, which is kind of a relatively high number, right? If you think about it. If you number, however, the carbons like that, 1, 2, 3, right to left, so you can do that, the OH group will be attached to carbon number 1. 1 is smaller than 3, so this kind of like right to left numbering will take the precedence. And in this case, we can say that, well, on carbon number 1, alcohol, right, suffix OL, the alcohol will be kind of like located, and then the OH group will be attached to carbon number 1, in other words, okay? So on carbon number 3, we'll have the phenyl, all right? So now let's put it all together. So we are going to have kind of like the position of the OH group and the root at the end of the name. So we can start with that, and then we can add the substituents to the left side of the kind of like alcohol part of the name, right? So what do I mean by that? So let's show the root first. So there is no right or wrong sequence to write the name, right? So you can start with the substituents, then continue with the naming or the like location of the alcohol. I prefer to start with the like root, right? So the root here will contain propan as kind of the part of the name, right? So because this alcohol is based on propane, right? 3-carbon alkane, propane, right? So propan will be the root of this like, name for this alcohol, right? So since we have the OH group, right? So we have the alcohol, we are going to have the suffix OL in the name as well. So the carbon where the alcohol all can be found is going to be carbon number 1. Carbon number 1 will contain alcohol, right? So 1 propanol will be on our hands. But this 1 propanol is not just 1 propanol, it is a substituted propanol. So because on carbon number 3, we have the phenyl. So let's put it this way, 3-phenyl. 3-phenyl, 1-propanol, right? So on carbon number 3, we'll have the phenyl. On carbon number 1, we have the alcohol, right? So, and then overall, all those things, such as phenyl and the OH group, are present on the propane backbone, right? So 3-carbon chain. All right, so good example, I hope. So now let's take a look at some more examples here. So I'm just like looking at some other options. Let's see. So we have here another one. So it's going to be pretty interesting to look at, I would say. What do we have here? So 5-carbon. So here we go, right? It's going to be the 5-carbon chain. All right, so let's switch gears a little bit and show something new. All right, so I'm going to erase everything here. Okay, so that's the continuation of our big problem. So, and here we go. Bear with me as I'm drawing the structure. And ethyl here. All right, so this one, right? So this chain, let's see how many carbons there are in the longest chain. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So then if we look at this chain, right, so 5 carbons, so we'll have this kind of like weird substituent that's going to be CH2 bromine. For this substituent, we don't really have like a name, right? It's going to be a little bit complicated to go with that. So it looks like it's going to be better if we consider this straight chain as our 5-carbon chain, which is still the longest one, right? So they both have 5 carbons, but this chain is going to be a little bit better because it's going to be what is going to be containing the substituents such as OH, right, ethyl and bromine. So we can easily name them as opposed to this like weird CH2 bromine if we consider this as a substituent, right? So in this case, like the more kind of less kind of like obscure chain or the chain with the less obscure set of substituents will win in our considerations, okay? So let's take a look. So we have the carbons here, so that's the 5 carbons in this chain, right? So substituent-wise, we have the OH, that's going to be our part of the alcohol group, right? When OH is attached to carbon, we have the alcohol. Remember, we're kind of drawing this like mushroom type thing. So then we'll have the ethyl, as well as the broma group in our chain as well. Right, so now in terms of numbering, so we can pretty much go 2 ways here, right? So in 2 directions, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, left to right or right to left. If you go right to left, carbon 5 will contain the OH group, which is going to be a relatively high number, as opposed to when we number the chain left to right. So in this case, 1, 2, and so on, carbon number 1 will contain the OH group, which is going to be better, right? So it will have a smaller, the OH group will have a smaller number for the carbon to which it is attached. Okay, so consequently, we're going to name the chain like that. 1, 2, 3, 4, 5. All right, so now let's see what we have. So 5 carbons in the chain. So what does it mean? So it means that the root will be pentane, right? So I just like to start with that, the root of the like respective like alkane or alkyl chain, right? So the respective alkane will be pentane, so the root will be pentane, and this will kind of like be used in the naming of our specific alcohol. So then clearly we're going to add the suffix or suffix "ol", right, to indicate that we have the alcohol. So the alcohol, so this is COH, will be on carbon number 1, or in other words, the OH group that will be part of the alcoholic functional group will be positioned on carbon number 1. Carbon number 1 will contain the alcohol, right? So, or the OH group will be attached to carbon number 1 to make alcoholic functional group. All right, so 1-pentanol will be like part of the name. So then more parts of the name will be there as well. So we'll have the ethyl as one of the substituents, and we'll have the broma group as another substituent, right? So now let's kind of put them in the alphabetical order. B, E, broma first, then ethyl. Bromo, ethyl. So where is bromo? So bromo group, right, is on carbon number 5. So let's signify that by making this notion, 5 bromo. On carbon 5, we'll have the bromine, right, or the broma group. On carbon number 3, that's 3, we'll have the ethyl, 3 ethyl. Carbon number 5, we'll have the broma, dash. Carbon number 3 will have the ethyl, dash 1-pentanol. 5 bromo, 3 ethyl, 1-pentanol will be our name with a full stop. Okay, great. So that's what we have for now in terms of the naming of those alcohols, right? So, and at this point, let's take a look at some kind of like other examples potentially, or we can move to other topics. All right, so let's see. I'm going to erase the board right here, and now it's gone. Okay. Okay, so what else do we have here? Let's take a look. Let's take a look. Let's switch gears. We'll still be in the naming, in the nomenclature realm, but we are going to take a look at phenols, right? So because some people are asking that question about like phenol, so they seem kind of almost the same. Yes, they are very similar. That's a good point, but they have like a significant difference. It's one letter difference, which makes these like words different, right? Phenyl, Y, phenol, O. So that difference makes different compounds, right? So now the phenol, so with an O, with the letter O, between N and L letters in the name will be looking like this. Let's draw like a typical phenol. Oops, sorry, Control Z. So that's your phenol, right? So it's not C6H5 anymore. C6H5 is phenyl, right? So that's substituent basically. So this one is a compound so by itself, right? It's not like attached to anything. It is just a separate, like standalone, independent, sovereign compound, if you will, right? So that's what it looks like. And it contains the phenyl, if you think about it, right? C6H5, but to the C6H5 here, an OH group is attached. So together, this combination produces a phenol. So phenol, so with the letter O. Underscore it, right? Put it on the piece of paper, plaster that to the wall or something. So now we have the phenol like this. So phenols can be substituted because we have, if you think about it, lots of like CH bonds right here in this like ring, right? So as we were talking about that at some point, so what happens in certain chemical reactions, so as you know, generally in chemical reactions, bonds are broken and then some new bonds are made, right? So that's a typical like, happening in chemical reactions. So here CH bonds theoretically can be broken, and then those hydrogens, right, that were attached to the carbons in this phenyl group, by the way, right, can be substituted with something like more exciting, right? Maybe some kind of like larger molecular, larger atomic groups, right? Different functional groups, and so on. And then we'll take and then we'll this way have like more interesting molecules that can be like served as maybe some kind of medicinal drugs, right? Or some kind of disinfectant agents, cancer treatment, and so on, right? So you name it. So yeah, that becomes kind of pretty evolved very quickly. So at some point, what we can deal with is a molecule like that, right? So here we have a phenol as our base compound, but this phenol will be kind of like heavily substituted, right? So we get rid of a bunch of hydrogens in this phenyl ring, and then we substitute those hydrogens with various substituents, such as ethyl, methyl, and another methyl. Okay, so here we go. So we'll have our phenol as our base name, right? So, but then this phenol will be substituted. So what do we need to do to kind of like make the name for this molecule? So we need to start numbering the carbons in the chain, right? So carbon number 1 will be the carbon to which OH group is attached, right? So then we'll be kind of like numbering either clockwise or counterclockwise, right? So we want to number in the way that will minimize the numbers of the carbons to which the substituents such as ethyl, methyl, and methyl are attached, right? So let's say if we are going to go clockwise, right? So this is going to be carbon number 2, 3, 4, 5, and 6, right? 2, 4, 6. So in this case, we're going to have 2, 4, 6 ethyl, and then we'll also have to have like methyl and methyl. We're going to have the dimethyl on carbons 4 and 6, right? So on carbon number 2, we'll have the ethyl. Okay, so 2, 4, 6, ethyl, dimethyl. Okay, so now another way to number it will be to go in a different direction, which is going to be the only other option, to go counterclockwise. Let's maybe mark it with the red color. So 1, 2, 3, 4, 5, 6. Okay, so here we go. We have a dilemma now. So we are going this way, 2, 4, 6. So what happens here? So in this case, so the sequence of the numbers will be the same, right? So we'll still have 2, 4, 6 clockwise, 2, 4, 6 counterclockwise, right? So, but the problem is that, so what happens is that if we use the kind of the black font right here, black font sequence, so on carbon number 2, we'll have ethyl, right? If we use the red font sequence on carbon number 6, we will have our ethyl, right? So in this case, the lower group alphabetically, ethyl, will have a higher number. So if we use the red sequence, if we use the black sequence, the lower group alphabetically, ethyl, right, precedes methyl. So the ethyl will have carbon, will have number 2 for the carbon to which ethyl is attached, right? So in this case, looks like the clockwise sequence will win over the counterclockwise sequence. So the alphabetical sequence will be the same, right? So ethyl, then dimethyl, di doesn't count in the alphabetical sequencing. It's only the names of the substituents, isopropyl being the exception, right? So then numbers, right? So on one hand, you can have the sequence like that. So on carbon number 2, sorry, it's going to be not this, not what I want. So let's use the black font, right? On carbon number 2, we'll have ethyl. On carbons 4 and 6, we'll have a total of 2 methyls. Okay, so the red sequence will be looking like this. So let's put it on the whiteboard as well. So 6 ethyl, and then we'll have 2,4 dimethyl. So let's take a look, right? So ethyl here will have a lower number. So here it will have a higher number. So then other groups, such as dimethyl, will have the number 4 and 6 and 2 and 4. So overall, if you look at this, so numbers seem to be the same, right? 2, 4, 6, 2, 4, and 6. But here, so this is going to be a better choice. So the first choice, because the group that follows alphabetically earlier will have a lower number. So that's going to be kind of dictating our choice. And then we're going to have to go with arrow number 1, or with this like black fonted part of the name, which will be a part of the total name of the molecule, all right? So that's going to be kind of our choice here. That's what we're going to stick with. Okay, so we have 2 ethyl, 4, 6 dimethyl. On carbon number 2, we'll have the ethyl. Carbons 4 and 6 together will have 2 methyl groups, right? So they will have to be distributed evenly between carbons 4 and 6. You cannot randomly have, for example, like 2 methyl groups on carbon number 6, and then carbon number 4 will have nothing, right? So that's why 4 and 6 are indicated in this name of the molecule, right? So then let's continue here. So what else do we have? So we have 2 ethyl, 4, 6 dimethyl, and finally we'll have the phenol, right? Phenol. Phenol will be part of the name here, right? So I use a dash here just to kind of like put the phenol part to the next line in my writing, but if you write it on the same line, then there is no need for the dash, right? So yeah, that's it. So 2-ethyl 4,6-dimethyl phenol will be our molecule name. All right. So now let's move on further. So now we're going to go to problem number 2, which will be devoted to the classification of the various alcohols, right? So we were looking at so problem number 2. Let's maybe change the font color a little bit. Go to blue, for instance, right? So here we go. So classification of alcohols, like one way to classify alcohols will be to look at them as the primary, secondary, and tertiary alcohols. So sorry, we'll take a break and then we'll come back. I'm going to pause recording. Okay, so we're back after a brief pause. So anyway, let's take a look at some example structures of alcohols, and then we'll just try to classify them as primary, secondary, or tertiary alcohols. So here we go. That's kind of going to be our first one, CH3, CH2. Then we'll have carbon like this with an OH group attached to that. And then we'll have a couple of methyl groups right here. All right, so here we go. Here we can see this carbon, right? So which in turn has the OH group attached to that. And then also this carbon in turn is attached to 1, 2, 3 3 other carbons. So if we have this pattern, then we are going to deal with the tertiary alcohol. So that alcohol is tertiary. So let's take a look at another structure, which will be looking like this: CH3, CH2, 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 OH. So here, this carbon has the OH group, right, attached to that. So then this carbon in turn has only one carbon attached to it, right? So in this situation, you are going to have a primary alcohol. So you see the carbon with an OH group surrounded by 3 alcohols, by 3 carbons, right? It's going to be tertiary carbon. So tertiary alcohol rather, sorry. So this carbon is surrounded only by 1 carbon, right? Consequently, we're going to have to deal with the primary alcohol. So 3 carbons around the alcoholic carbon, tertiary alcohol. 1 carbon around the alcoholic carbon, primary alcohol. So last but not least, secondary, of course, right? That's the only thing that's missing in our mini review. So this is going to be our alcoholic carbon. Let's not mark it, right? But we can see the bonds here, right? So between this alcoholic carbon and other carbons. 1, 2. Okay, so in this situation, we're going to look at the carbon that is attached, the alcoholic carbon with an OH group. This carbon is attached in turn to 2 other carbons, right? So if it is attached to 2 other carbons, we are having the secondary alcohol. So you see 3 carbons around, tertiary. 1 carbon around, primary. 2 carbons around, secondary. That's it, right? These are our like comprehensive, I hope, examples. Okay, so now let's move on. So we're going now to take a look at the connection between the chemical structure of alcohols, right, of some kind, and their physical properties. So that's going to be, I think, problem number, what, 4, perhaps? Hopefully I'm right. So we're going to try to take a look at several structures, and we will be arranging them in the order of increasing boiling point, right? And the structures will be ethanol, which is going to be CH3, CH2OH, methanol, CH3OH, and 1-propanol. CH3, CH2, CH2, OH. So yeah, we can name them, right? You can name them for yourself. So this one is from methane, right? So which lost 1 H and then it was swapped to an OH, right? So we have methanol. So this is going to be just like ethane that now got 1 H removed and this H was substituted with an OH. So we have ethanol. So this one is 1-propanol. So because carbon number 1 will contain OH, since carbon number 2 can also contain OH, but it's going to be a completely different compound. That's why we need to like resort to the number in here, right, to show the difference between the isomers that can be kind of like realized in this structure, right? So here we have 1-propanol, right? So let's take a look at the order. We'll try to arrange them in the order of increasing boiling point, right? They all have the OH group, so like only 1 OH group, so it will not really kind of like matter like in terms of the strength of the aggregate hydrogen bonding that can be kind of, for example, stronger if we have like, let's say, several OH groups, right, in the molecule as opposed to just 1 OH group. So all the molecules will contain only 1 OH group. It's not really like going to be a distinguisher, right? So it will only tell us that they will have relatively higher boiling points than corresponding alkanes that don't have the OH group, obviously, right? So next, we look at the kind of like number of carbons in the chain. This is a different number from compound to compound. We have 1 carbon, 2 carbon, and 3 carbon chain. Remember, as we were like increasing the number of carbons in the carbon chain when we were looking at alkanes, we said that the more carbons there are, the higher the strength of the dispersion forces between the molecules of the corresponding alkanes, right? With like lower or higher carbon chain, right? So yeah, basically, the higher the number of the carbons in the alkane chain, the stronger the dispersion forces between those alkane molecules will be, and the higher the boiling point will become, right? So, such as, for example, the boiling point of, let's say, heptanol, or no, not heptanol, but heptane, 7 carbons, will be much higher than the boiling point of, let's say, ethane, 2 carbons, right? So because in heptane, so stands for what? 7, right? We have 7 carbons. 7 carbons in the chain will provide us with higher strength dispersion forces that will exist between heptane molecules, as opposed to the dispersion forces that will exist in a shorter chain ethane molecule, right? So between like other molecules of ethane. So in this case, so the more carbons in the chain will have, right? So the higher the dispersion forces will be between the corresponding molecules. And then the higher the boiling point will be, meaning we'll have a higher temperature need in order to separate those molecules, which are kind of like stronger, quite strongly bound to one another. So we have the same trend here, right? So if we take a look at this compound, it only has like 1 carbon in the chain, right? Potentially methanol will be our lowest boiling point, right? So let's say it's going to be like, for the sake of the example, maybe like 10 degrees Celsius, right? Like pretty low number overall. So 10 degrees Celsius boiling point. So then we'll have again, so other compounds. So this one has 2 carbons in the chain. So presumably this compound will have stronger dispersion forces, right? From the dispersion forces perspective, of course, they will all have hydrogen bonding, right? So that will be there for sure. But this compound will have stronger dispersion forces because it has more carbons in the chain. So consequently, ethanol will be kind of like having a little bit higher boiling point than methanol. So maybe let's say 20 degrees Celsius for the sake of the example, right? So finally, this compound will have the 3 carbons in the alkane chain piece of the molecule, right? And it will have strongest dispersion forces. And then this will be reflected in the highest boiling point, right? That will be ascribed to the molecule of 1-propanol. So maybe it's going to be like, let's say 30 degrees Celsius boiling point, right? So because it will have the highest number of the carbons in the alkane part of the molecule. All right, so that's what we have in terms of the trends for the boiling point here. So now we're going to draw the structures, right, of the products. So we're going to look at the chemical reactions. So far, in our considerations, we are going to consider the dehydration of alcohols, right? So let's just remove everything, and then we're going to, I guess we're going to conclude at this point. So with problem number 5, which will be about dehydration of alcohols. So we're going to focus on that. Remember, so hydration, that's going to be a related term. So how does hydration work, right? So that's when you have alkane, no, sorry, not alkane, but alkene rather. So it's a hydrocarbon with a double bond, one double bond between 2 carbons, right, in the chain somewhere. So then alkenes can be hydrated, means that the double bond in alkenes, the carbon-carbon double bond in alkenes, will be able to react with the molecule of water to form alcohols, right? So that's going to be the hydration. So you add the water to the alkene in these circumstances. So dehydration, that's when you remove the water from where? In our discourse is going to be you removing the removal of water from the molecule of an alcohol of some sort, right? So that's what we are dealing with. So now let's take a look at some specific examples and see what's happening, right? So here we go. It's going to be looking like this. So we have some kind of like branched alcohol, pretty exciting. So let's check it out. So we have CH3, CH with an OH on it. All right, so let's consider the structure, and then we are going to perform the dehydration of it, right? So dehydration, so it's going to be a good idea to show the conditions, right? So the temperature is 180 degrees Celsius, and then it's going to be like performed in the presence of H2SO4 as our additive or catalyst, in other words, right, for the dehydration reaction. So dehydration, so we need to consider two carbons, right? So it's going to be carbon with an OH group on it, and then the adjacent carbon with a hydrogen. So here, adjacent to the alcoholic carbon are two carbons, CH and CH3, right? So both of them possess a hydrogen that can be removed alongside OH during the dehydration process to produce HOH or H2O as a byproduct. Okay, so now here are a couple possibilities that can be formed, right? So check this out. So let's say track those carbons, right? So left to right in our example. So let's say we're going to remove the carbon, we're going to remove the hydrogen from this carbon here, which I'm trying to kind of point at. And then as a result, we are going to have something like this. Oops, sorry, the battery is about to die. I need to recharge. All right, so we are back. So here we go. So let's just draw the structure of the resultant products, or rather products, because we'll have two isomers that can be formed. Okay, so let's just now kind of like follow the original structure. Instead of CH3, now you remove one H, right, from the carbon adjacent to the alcoholic carbon, and you're going to have CH2. Right, so CH2, then it has, this carbon now has two H's only, right? Consequently, we are now going to have the double bond, right, to make to fulfill the four valences of the carbon, right? So this carbon now is going to lose the OH group, right? It will be now CH with a double bond correspondingly, right? So yeah, because remember we are making the bond, right? So from the electrons which are liberated after the removal of H and OH respectively, right? So these electrons, let's say, so imagine there used to be like a CH bond, right? So now H with its electron was removed and the carbon with its electron was left over. From this carbon, OH with its electron on the oxygen, obviously, was removed, and then the carbon, this carbon with an electron was left over. So now the electron on this carbon and the electron on that carbon will make a new bond, right? So that's why now we have not a single bond here, but a double bond. So we have another bond formed in addition, right? So then we are going to redraw the remainder of the structure, right? So CH, CH, and a couple of metals will be remaining. So now, another possibility is that we're going to form an isomer, right? So now we're going to remove the OH from here and the H from there, from this carbon H will be removed. So what's going to result? The following structure will be produced. Sorry. So this is CH, right, which is going to lose hydrogen. So consequently, it will be kind of like forming the carbon, just the naked carbon, like without any hydrogens. All right, so that's the one. So check the valences. 4 valences around this carbon, 4 valences around this carbon. Okay, good. So we are in a good shape. So these are our 2 isomers. If you look at the structures, right, so they have the same count of carbons and hydrogens, but the like attachment, like where the double bond is, right, for example, is different, right? So then those things will be isomers because the order of the like atoms, how they are connected to one another is different from, let's say, this molecule to that molecule, right? So these are our isomers. So now let's take a look at the prevalent product, right? So which one is prevalent? So you may ask this question. So if we take a look at this situation, right? So the carbons which form a double bond only contain 1 carbon total attached to them. It's going to be this one, right? So this carbon has only H's, right? This carbon has H and another carbon attached to it, right? So 1 carbon is attached here. So in this situation, we're going to have again the double bond, right? CC double bond. And now to that CC double bond, so a total of 1, 2, and 3. 3 carbons are attached total to this double carbon-carbon bond, right? So 3 carbons are attached. So according to Zaitsev's rule, so the alkene that will have more carbons attached to its double carbon-carbon double bond, right? So the alkene with more carbons attached to the carbon-carbon double bond will win, right? So this alkene will have 3 carbons total attached to its carbon-carbon double bond. Consequently, 3 is more than 1. And then this is going to be our chief or major product, right? In other words, major product will be this one, this alkene structure, right? So now let's move on to some kind of like other examples, right? So we're going to take a look at what else. So let's take a look at some more possibilities here. So it's going to be another, let's take a look at some cyclic structure, right? So just for the challenge of it. So it's going to be like that, right? So again, cycle. So this one is like nothing crazy here, right? So if you look at those like bands, right, or the angles, vertices, whatever you might call them, they will all be representing carbon. So carbon, carbon, and so on. So you have like 6 vertices here, 6 carbons, right? So then each carbon will have already like 2 explicit bonds shown, right, at them. So consequently, so we are going to beef them up with what? With hydrogens, right? So if it's nothing is shown, if nothing is shown, then we assume carbons and hydrogens, right? Carbons, again, are tetravalent. So consequently, each carbon here will have the 2 H's attached to it. CH2, CH2, and then 6 times, right? So then we might have the substitution going on, right? So just like in a straight chain alkene, straight chain alkane, in the cyclic alkane, we also have substitution, right? You remove 1 H and then you substitute it with something kind of more exciting, like different, right? So some kind of like OH group, for example, right? And then maybe a methyl group, right? So, and then you have like a brand new molecule right here. So now we are going to do the dehydration of this alcohol. By the way, this alcohol has the carbon, right? The alcoholic carbon, this like the one that forms COH functional group, known as alcohol. So this carbon has 2 carbons attached to it, 1 and 2. Consequently, it's going to be a secondary alcohol, by the way, right? Speaking of which, so now with the addition of H2SO4, sulfuric acid, and the highly elevated temperatures, 180 degrees Celsius, we'll be able to perform the dehydration of the alcohol. We're going to form the water, HOH, and the alkene is our like main product, right? The organic stuff. Okay, so if you consider the situation, we have the H here, right? And we still have the H here. So there are 2 adjacent carbons to the alcoholic carbon, right? So from which the H can be removed, and then like depending on which carbon you are removing the H from, you will have 2 isomers, right? So now let's draw both of them. The sort of like 6-membered chain will be retained. Oh, sorry. So there's going to be no more OH. So this will be gone, right? So now you're going to have CH left over here. And then let's say you're going to remove this hydrogen first, right? So then you are going to have like carbon with the lone electron, like somehow somewhere like in the intermediate stage left over, right? And then once the OH group is removed, there will be a leftover electron on that carbon as well, right? So together those two electrons will be able to make the new bond. That's why we are making the alkene, right? So this CH with the methyl group, right, will still be left over in this isomer, right? So now let's take a look at another possibility. Another possibility is that we're going to switch colors. We're going to remove this guy, right? So this red what's it called, the red hydrogen, right? So now let's see what happens. So another isomer can be formed, right? So once we assess the final structures, we'll be able to confirm whether or not we have the isomers, as a matter of fact, right? So this H stays, OH is gone as well, right? So at some point, at some intermediate point, the OH with an electron will be left over, and the carbon with its electron will be like remaining, right? As well as this carbon, right, will also lose H with its electron, but the carbon will have the CH3 remaining, obviously, and then the carbon will have also the electron remaining, right? So together, those two electrons on these carbons, right, which lost something, will be able to form the double bond, right? If you look at this structure, right, so you're going to have different structures, right? So double bond, single bond, methyl. So double bond, methyl, right? So clearly the positioning of the double bond relative to, let's say, the methyl group is different, right? So here it's kind of like right next to the methyl group. In this case, it's a little bit farther from the methyl group. So these two compounds will be isomers. They will contain the same, they will have the same molecular formulas, right? Meaning the count of the carbons and hydrogens will be the same for those two molecules, but the kind of like sequence of the like building blocks is going to be different here, right? So different positioning of the double bond, for example, you can think about this way. So different positioning of the double bond will make those two compounds isomers, right? They will not be identical, they will be isomers rather. So yeah, and that's what we're going to have here. So now let's take a look at the major product. So if you look at the situation, maybe let's take a look at some different colors. So there is a carbon-carbon double bond, right? So there is a hydrogen here, hydrogen there. So now what about the carbons attached to that carbon-carbon double bond? One carbon, second carbon. What about this situation? So in this situation, we're going to have the following. Switch colors, maybe, I don't know, like let's do dark orange, or let's do maybe like purple, right? So we have the carbon number 1, then we'll have carbon number 2 attached to the carbon-carbon double bond overall, and another carbon which is attached to the carbon-carbon double bond, right? So here, and then here there is obviously a hydrogen, right? So in this situation, we are going to have 2 versus 3 carbons attached to the carbon-carbon double bond. So 2 is, I mean, 2 is less than 3, or 3 is more than 2. So consequently, this is going to be our major product, right? So because this product has more carbons, more carbon atoms overall attached to the carbon-carbon double bond than the product on the left. So major, according to Zaitsev's rule, more carbons are attached to the carbon-carbon double bond in this situation. So, and yeah, so at this point, I think this is enough. So that's been quite a session, but I thank you for your attention and have a good day. Bye, everyone.